Here we have an elliptical path, and it would be easier to see that it is an elliptical path if we actually divided this whole thing by 64, because then we would get x squared. 16 over 64 simplifies to 1 over 4 plus y squared over 16, and that's equal to 64 divided by 64 is 1. This is our standard parametric form that Cartesian form that we're used to when it comes to ellipses. And we could convert this to parametric form if we want, but it turns out that using this form is going to be the easiest form to work with when finding dy dx Cartesianally. So to find dy dx, we have to take the derivative of each piece. So first, we're going to do the derivative of 16x squared, which is 32x. And I'm going to rewrite this because this is a mess, because I was trying to show the connection here. So one sec. Okay, so we are taking d dx of 16x squared plus y squared equals 64 by taking a derivative of each piece. Okay. So first, derivative of 16x squared is just 32x by the power rule. Okay. The derivative of y squared is going to be 2y times dy dx. Okay. Whenever we're taking a derivative of a function of y with respect to x, we have to attach this dy dx because it is a chain rule. The derivative of blah squared is always going to be 2 times blah, but now we have to multiply by the derivative of that inside, which is dy dx. Same thing here, the derivative of 16 blah squared is always going to be 32 blah, but we have to multiply by the derivative of the inside function with respect to x, but the derivative of x with respect to x is just 1. Dy dx we don't know, so we have to write that. Okay, and that's equal to the derivative of 64, which is 0. So now we're going to subtract our 32x to the other side. We get 2y dy dx equals negative 32x. And now we just need to divide by 2y. So we get dy dx equals negative 32x divided by 2y, which simplifies to negative 16x over y.